The following is a presentation of the Six Arrows Radio Network.
This week on the Workbench, all about oscilloscopes, Part 1. Stay tuned. Welcome to the Workbench. I'm your host, George, KJ6VU.
And I'm Jeremy, KF7IJZ.
The Workbench is sponsored by CADSoft, makers of Eagle PCB design tools. Get your free copy at cadsoft.io. And by MCM Electronics, where I can and you can buy all of your electronic parts needs and equipment. Check out mcmelectronics.com today.
Hey guys, welcome back to the Workbench. George. All right, George is asleep because we started recording 4 hours ago. Actually, yeah, exactly 4 hours ago.
Was that still the same day?
No, it is another. Well, for you it is. For me, it's tomorrow. For you, it's still today.
We had an awesome interview.
We did. Absolutely awesome. And in fact, we got, don't worry, we already run long. We're not going to put all 4 hours of content out. We're actually going to get that edited down. And today you're going to be listening to part 1 of a 2-part episode with our first ever guest on the Workbench podcast. Today we were joined by Alan Wolke, W2AEW, who is a ham and field application engineer for Tektronix. I became aware of Alan because he has an amazing channel on YouTube all about oscilloscopes and spectrum analyzers and test equipment and how to use these things and how to learn about them. And it's a wonderful treasure trove. And I thought he would be the perfect person to come and talk to us about oscilloscopes. You can find him on YouTube at youtube.com and searching for Whiskey 2 Alpha Echo Whiskey, and his channel will come up. And of course, as always, we will have links in the show notes. Alan was also kind enough to go through his billions of videos and pick out a selection that he thought would be really topical for folks who are new to oscilloscopes.
And he's got tons of good information, and he's really a awfully nice guy and willing to spend a lot of time with us. And it was just really interesting. Some of the oscilloscope topics go pretty deep. And if you don't know what a scope is, you'll learn that, but you'll also learn a lot of in-depth information about how they work and some of the more esoteric features and specifications of the scopes.
Now, I'll point out, we're going to do things a little bit differently this episode. We're not going to have a kind of our intro news items or talk about the bench because there is a ton of content we want to get through. We're also not going to do Q&A this week to try to be as respectful of your time as possible, which I know, given our past performance, is probably not something you believe, but I promise we're trying. A few items we do need to take care of. And first of all, we have a winner for the MCM Electronics DMM giveaway.
Oh, wow. Who is that?
That is Andrew Roan, Kilo Echo 8 Papa. Andrew, you are the proud owner of a 22,000 count true RMS computer connectable digital multimeter from MCM and Tenma, and they will be getting that out to you shortly. So thank you to everybody who participated, and thank you to MCM Electronics for sponsoring that. Please remember that if you want, you can save 5% on your next order from MCM Electronics by using the code RADIO5 at checkout. That's RADIO, the number 5 at checkout. And keep an eye out. We may have more giveaway surprises from MCM Electronics in the future.
Yeah, they were awesome. That was very nice of them to do that.
Indeed. Other items to take care of. Is there anything else we need to take care of?
No, I think that's it. Let's just get right into it.
All right, let's get into it with Alan, Whiskey 2 Alpha Echo Whiskey. So, George, we have a very special guest with us this week, and I am very excited. We have Alan, W2AEW. Alan is most known for a very successful and popular YouTube channel under his call sign, W2AEW, where Alan really breaks down oscilloscopes and other test equipments, and he has been gracious enough to join us this evening as we deep dive on oscilloscopes. Alan, welcome to the Ham Radio 360 Workbench podcast.
Well, thank you for having me. I enjoy being here.
All right, Alan, if you would quickly give us a little bit of background about why you are such an awesome person to have on to help us understand oscilloscopes this evening.
Well, you have to tell me that, but I'll give you a little background. So, well, I've been a working engineer for 31 years. And the first 21 of those years, I was had what I call a real job. I go to an office or a lab every day and push buttons and twiddle knobs and play with oscilloscopes and the various roles and jobs that I've had, from everything from hard disk drives to fiber optic communications. About 10 years ago, I took a job as a field application engineer with Tektronix, probably the world's best known oscilloscope manufacturer. Even though my role with Tektronix is primarily on the RF side of things, I play with scopes every day with Tektronix as well, and supporting customers that use these products. So I've been a scope pilot for a long time. Even back in high school, I worked in a TV repair shop and learned how to use an oscilloscope on an old Tech 465B, which is probably one of the most popular 2-channel 100 megahertz analog scopes that was ever made. So it's a bit of a passion of mine. I've got more scopes that I can count on one hand down in my basement lab, and I use them all the time. So I don't know if that qualifies me, but that's a little bit of background.
Well, that certainly qualifies you more than me. My qualification to talk about this subject is, as a kid watching Mr. Wizard. Mr. Wizard had an oscilloscope, and I didn't understand what it was when I was 7 years old, but I knew that one day I wanted one.
Okay, well, there you go. That works.
So if you would just give us a quick overview about your history and career as a ham as well.
Sure. I actually got my original ham radio license in high school. The electronics elective teacher was a ham and formed a radio club in the high school. And I think it was to get free student labor to put up antennas in the courtyard. But we all got at least our novice license then. I had gotten my novice license then, 5 words a minute novice. And we all built a QRP radio setup. And it was like 5 different little mini kits, point-to-point wired kits, like a power supply, an antenna tuner, a VFO, a transmitter, and a receiver. And that was a lot of fun, and certainly I learned an awful lot. But I got out of high school. I didn't have, any money to get any other equipment besides that, and really wasn't practical for me to bring that radio to school at NJIT, where I went. There wasn't really much place to set up an antenna or a radio in Newark, New Jersey. So I kind of dropped out of the hobby for a while and didn't get back in until probably 15 years ago. And I had to start over. So I came in as a tech, and then a tech plus, and then I held an advanced license for a while, and then upgraded to extra ultimately. And then, a few years after upgrading, I'd gotten the W2AEW vanity call sign, because that's my initials. And I figured when I get a little old and stuff starts leaking out of my head, I should still at least be able to remember my call sign. So I do a little bit of home brewing, but most of my ham radio activity these days is a little bit here from the shack, just on HF primarily, and a bit of HF mobile when I'm out running around for my job.
Well, based on how many videos you have on your YouTube channel, I think you might also suffer the same problem that George, myself, and Cale have, in that I spend more time doing podcast as ham radio than I do on the air these days.
Yeah, that too. I mean, when I first started putting the channel together, my goal was to do a video a week, and I did that for about the first 2 years, and then things changed, and I wound up doing a video every week and a half or 2 weeks. And one of the things that changed is I got a dog who likes to walk a lot. So now I'm down to 1 or 2 videos a month typically, but I think I've got 242 videos up right now. 242, 243, something like that. But I get about 5,000 views a day, so there's still a lot of people that are discovering the channel for the first time.
Well, and we'll have a link in the show notes to your channel, which if you go on YouTube, you can search for W2AEW. And then Alan has been kind enough to actually pick out a selection of videos that will be really topical as we introduce the topic of oscilloscopes. So with that, George, where should we start?
Well, I think we should start with the basic definition of what a scope is. So maybe, Alan, if you could kind of rewind back in time and maybe talk a bit about what the origin of the scope was and what basically you could do with it.
Sure. Well, I mean, the origin actually goes back pretty early. Carl von Braun and a couple of other folks had done some work, and some of the early tubes that emitted electrons and lit up phosphor on the inside of a vacuum tube, they called it radiant matter. And then some folks eventually started to figure out how to control that beam. And I guess probably the first commercial working oscilloscopes actually probably date back to the late 30s, early 40s. And you got folks like Alan B. Dumont and other companies that had done some things. So basically what a scope is I like to tell people it's kind of like a graphical voltmeter. It allows you to look and see how voltages vary versus time. So there's essentially a beam of electrons that is sent to, let's talk about the analog scopes to start off with. A beam of electrons that's sent to the face of a CRT or cathode ray tube and traced across that screen at a constant rate. And then a voltage that you might be testing will drive that beam up or down. And the phosphor on the screen will glow and persist for a little while and effectively trace out what that voltage looks like over time. So in a sense, that's what a voltmeter is. I mean, if you took an old Simpson 260 analog voltmeter and put a pen on the end of the needle and ran a piece of paper across it and traced out how a voltage changed over time, that's essentially a paper equivalent of what an analog oscilloscope does.
So a scope is really one of the most fundamental basic instruments we might have in our ham shack lab.
Yeah, I would say outside of some kind of a VOM or DMM, a scope really becomes in my mind almost an essential piece of your bench.
So if you're a ham and you're going to be building some projects, what would be the typical use for a scope? So what would you want to measure the voltage and see that voltage over time?
Well, I think some of the very basic things is, hey, I'm building this radio and I've got a little power supply hum. You might actually want to go and probe your power supply to be sure you've got adequate filtering to get rid of any ripple that might be on that power supply. If you're doing some kind of a rig with, maybe single sideband or AM, you might want to, trace out the audio path from the microphone through a preamp, through maybe a power amplifier or a modulator to be sure that the voltages are clean, they don't get distorted. They're really great for troubleshooting. Anytime you're building something, where does my signal go awry? My signal looks good here. Nope, it doesn't look good here. And is that because of a design problem or a component problem or something like that? But being able to visually see what those voltages look like can be real helpful. I mean, I don't know. Oh, I'm sorry. Go ahead. No. I was going to say, I don't know about you, but I visualize how circuits work almost by thinking about voltages being as different elevations. So this voltage is above that voltage, this is below the power supply rail, these types of things. And being able to visualize that on a scope screen just naturally fits in the way that I think about how circuits work.
I think I can add my 2 cents on that, because when I got my first scope, at the time I had an Arduino that I was excited that I was getting it to blink an LED. And of course, hooking the probes up to see what was happening to make the LED come on and off. It was basically, there was a a horizontal line that was just jumping up and down and up and down. And then as you start playing around with some of the pulse width modulation things in the Arduino to be able to get the LED to, blink on and off and change the intensity of the light, I was able to hook the scope up, and I was seeing that there was a waveform in the bar. The peak would get wide and then narrow, wide and then narrow. And for me, it really helped bring these concepts together in a way that I could understand them, because looking on the scope, I was actually seeing visually what was happening. I was actually seeing the modulation of a signal. And for me, it made things click.
Well, that's for sure. Yeah, because otherwise it's like a little black box. You really don't know, especially like in audio circuits. I found a lot of times that you'll hear some distortion, and when you look at it with a scope, you can see exactly what's happening, and that'll make it easier to kind of figure out where to start to address the problem. But without that, you're really kind of shooting blind.
Yeah, because a multimeter will only take you so far, and by being, like you said, being able to see it, the bottom of this waveform is being clipped. And why is that? Do I not have this transistor biased at the right point, or do I have the wrong component value in there, or something like that? Being able to visually see those things just, really shortens that troubleshooting time.
This is something I know you have countless examples on your YouTube channel that people would be able to watch of you actually using a scope and looking at different circuits and actually seeing how things react. Yeah,
a lot of what I tried to do is, the hump that people have to get over sometimes is in order to be able to use the scope to, visually see these signals and have confidence in what you're measuring, you got to know how to use it in the first place. You got to make sure that I'm driving the scope right so that the scope isn't lying to me, right? Because the scope's not going to tell you if it's lying to you. Like if you set up something wrong or something on the scope and the waveform looks weird because of that, the scope isn't going to tell you that. So you've got to learn about how best to use the tool before you can interpret what the tool is telling you.
Well, and with that, one of the things that I think, at least for me, is that you mentioned the venerable, was it the 450B, correct? The Tektronix 2-channel?
Oh, the old 465B.
Sorry, 465.
Probably one of the most popular 2-channel analog scopes that certainly that Tech ever made.
And these are things that if you go to Dayton and other Hamfests, you still find these aplenty. And I remember, like a lot of other test equipment that's from 20 years ago, but it was really high precision. You're finding these things for $100, $200, $400 for some older equipment. And in the world we live in today, you can actually now buy fairly featureful low-end scopes for about $400 that are digital and have a lot of features. So I think it would be good if we start talking about what does somebody look for in a scope, and probably the first place to start is analog versus digital. Because again, I can go out and spend under $400 and get a 50 megahertz 4-channel scope from Regal that has a lot of math functions and storage and a lot of memory depth to be able to capture and replay waveforms. Or I could go out and spend about $100, $150 on one of these 465s that have actually been well maintained and still calibrated at my local Hamfest. So how, as a new ham, somebody new to owning an oscilloscope, decide which direction to go down?
That's a great question, and not one with a clear answer, because there's really good reasons for both. I think, usually if someone is just a hobbyist and they just want to look at signals, learn about what a scope can show them, maybe they want to monitor the RF output of their transmitter or something like that, I recommend go in cheap. Go for a $50 or $100 Hamfest analog scope. You'll learn an awful lot about how a scope works. You'll learn about things like trigger circuits and how the triggering works and what does it mean to have a different time-based setting. And really get a good feel for things without falling into a potential trap with some of the digital scopes where you might be aliasing a signal and the scope is kind of lying to you. Okay, that really doesn't happen with the analog scopes. Another thing with the analog scopes is that being able to look at, like a modulated RF envelope, like an old station monitor, just about any analog scope it will do a really great job at that. And not all digital scopes will. And you can get into them, like you said, pretty inexpensively, especially these days, since there are so many low-cost digital scopes out there. A lot of people are just getting rid of the analogs because, they've outgrown them and they want some of the features that the analog scopes give you. So there's almost, you can always find some pretty decent, even, laboratory grade, analog scopes out there. And it's a great place to learn. The digital scopes certainly have a great place, and especially if you're doing things like projects with Arduino or digital interfaces and things like that, where the capture and storage and being able to do single shot capture to analyze, some digital waveforms, maybe a packet of data being sent over a bus or something like that. You can't really do that with the analog scopes. some of the automated measurements that you get along with the digital scopes, require you to do more math and thinking, and counting of divisions and that kind of thing to measure things like frequency or amplitude or rise time or something like that with an analog scope, whereas on a digital scope, it's a button push. Okay.
So you just introduced in that last 60 seconds, like 400 topics that I think we need to pull a little bit on. Some things that jumped out is you mentioned triggering. Explain to folks, what is triggering and what is that used for?
That's a great question, and I think it's kind of a two-part answer. Okay. On the old analog scopes, a trigger is something that would kick off the sweep of that beam across the screen. Okay. So think of it like a trigger on a gun, right? You're initiating the firing of a bullet. In this case, you're initiating the sweep across the screen. So you can set up a trigger to say, hey, trigger whenever the voltage at this input crosses above a half a volt. So if I've got a repetitive signal, as soon as it goes from below a half a volt to above a half a volt, the beam gets kicked across the screen and it traces out the voltage from that point. What that does for you is it helps to stabilize that waveform, because now if you've got a signal that every time it crosses through that same voltage, you're always starting the trace at that point, the signal is going to always start at the same point and is going to be stable on the screen and not roll back and forth in kind of an unsynchronized manner. So that's really what the trigger on the old analog scopes is. Now on a digital scope, it's effectively the same thing, but I more call it on a digital scope kind of like a marker, okay, or a bookmark, because today's digital scopes are sampling data all of the time. So when I set up a trigger, all it does is it picks that trigger condition to be at a particular spot on the screen, but you have the ability of seeing what happened before the trigger as well as after. So you get what we call pre-trigger information. So let's say the event or the thing you want to trigger on isn't the first thing that happens. Maybe you want to see what led up to that trigger point. You can do that with the digital scopes. You can't do that with the analog scopes. So the trigger is a bit more of a marker saying, the scope is always capturing data. It's always sampling the data. As soon as it gets the trigger, that tells the scope, okay, keep this amount of pre-trigger information that you already have, and then grab the rest of it after this and then display that on the display. So it's kind of a marker to tell the scope what event to grab to put on the screen for you.
Now, we're talking about the display of an oscilloscope, and one of the other terms that you used is you talked about the time divisions. And one of the things that we probably should cover is, obviously on the screen of an oscilloscope, there is an X axis and a Y axis, and you're plotting information against those axes. Can you explain what each of those axes are? Sure.
So think of it as it's a grid. It looks like a checkerboard, usually 10 by 10. Some scopes have got 10 by 8 or something like that, but there's a fixed number of grids. If you think about the vertical lines, they're dividing the screen, in 10 kind of horizontal or vertical bars across the screen horizontally. And when you set the time base on an analog scope or the horizontal scale on a digital scope, you're usually setting some time per division. And what that says, like on the analog scope, is how long is it taking that electron beam to go from one of those major division lines to the next. So if I set it to 1 millisecond a division, that means it's taking a millisecond to draw from one of those vertical lines to the other. So if I had 10, vertical divisions or, 10 grids, if you will, it would take, say, 10 milliseconds to go across. So on the digital scope, it's the same thing. Even though we're not moving a beam, it still represent a representation of time, for that waveform that's varying. Similarly, the horizontal lines, divide the screen into 10 vertical, or maybe 8 or 10 vertical sections. And then the vertical controls, you're setting essentially the sensitivity of how much voltage does it take to move the beam up or down. So you'll set it usually by some amount of millivolts or volts per division. So if I set it to, say, a half a volt per division, and I hooked up a 1 volt signal, that would move the beam 2 divisions up from the baseline or ground. So it really is, the grid lines are kind of your measure of time horizontally and voltage vertically.
So it sounds like, if I'm understanding this correctly, that effectively you have you obviously you have a fixed amount of screen real estate, and on the scopes you can adjust how much, or I guess how, like for instance in the horizontal demarcations you can set how much voltage is shown at each one of those lines, and for the vertical ones you can set how much time is set there. So if you have a wave event or something that takes only milliseconds versus ones that take seconds, you are adjusting the time base to make sure that you can see those.
That's exactly right. You have to think about the frequency or the rate of change of the signals that you're looking at to set that time base or to set the horizontal scale. If you're dealing with audio circuits or audio signals, it's very common to have that horizontal scale or horizontal time base set to maybe a millisecond a division, or maybe a little bit slower than that, like 2 or 5 or 10 milliseconds a division, maybe a little bit faster to 500 microseconds a division, depending on what you want to do. Oftentimes, if I'm using the scope to look at the single sideband modulated envelope of my transmitter, I'll set the scope to somewhere between a millisecond of a division to maybe a half a millisecond, 500 microseconds a division. It gives you a good view of several audio peaks as you're speaking. Whereas if you make the scope too fast, it looks like the whole thing is just wobbling up and down, and you don't get a really good view of the peaks and valleys. Where if you go too slow, especially on an analog scope, if you go to 2 or 5 or 10 milliseconds a division, the screen might start to just not update fast enough, and you get a little bit of flicker or blanking, if you will, between traces. So there's always a trade-off, but it all depends. If you're dealing with, say, looking at the a local oscillator of a rig that you're building that might be operating at a couple of megahertz, you got to think, okay, that's a couple of megahertz. I might need to bring the horizontal time base up to, a microsecond a division or a half a microsecond a division in order to be able to see that signal.
So I'll ask both of you, because with my digital scope, I have noticed before, you kind of, one of two things. You either have to have a rough idea of what the voltage range is and the periodicity of a wave that is periodic, meaning it repeats the same pattern over and over again to dial in those settings, manually. But my digital scope, which is again a relatively low-end modern digital scope, also has an auto-ranging button, which will go through and try to figure that out so it locks that waveform on the screen. On analog scopes, is there a feature that will do that, or does it get back to really understanding what it is you're trying to look at and dialing those things in on your own?
You're going to be sorry you asked me that question because because I call that auto set button the wimp button. You don't know how to drive, get out of the seat. No. But
wait. Hold on. This is important because this gets into ham radio philosophy. Just so you know, I'm one of those stinking no code hams that got my license in 2009. So does that mean I'm not a real ham?
Absolutely not. So, but it's funny because before I joined Tektronix, I was pretty good friends with the Tektronix sales guys as well as the Agilent sales guys and things like that. And when they'd come in to demonstrate a piece of equipment, they'd hook up their little demo board and they'd hit that auto set button. And I'd always they always hear something from me when they did that. But but the reason I say that is because I encourage people to really understand what that button is doing for you. You're better off really getting a good understanding of what you expect that signal to look like. Where should it be? You know what the voltage rails of the circuit is. You can kind of start with your vertical settings that way. You should have a pretty good idea of what the signal frequency is, if it's in kilohertz or megahertz or whatever it is. You have a good idea where to start, because there may be an aspect of the signal that the auto set feature doesn't lock onto. And you don't really know what changes or settings the auto set has done for you if you don't pay attention to what it did to all the various settings. So it means that you're just going to be less efficient moving forward to when you really need to adjust the scope to look at a particular detail.
Actually, I can vouch for that because half the time, even in periodic waves, my scope, when you press that button, it'll get you at least dialed in where you'll see the waveform start to roll, meaning it won't lock. As you were talking about, but it gets you in to be able to dial in a little bit more. Now, another question that I have, one thing that we're talking about digital scopes, but really, I think the modern term, for the most part, or at least a lot of the ones that are going to be the bench tops, like if I start talking about the Regals or you move up into what are now the Keysights or the Tektronix, I think they're more accurately referred to as a digital storage oscilloscope. Is that correct?
Yeah, generally that is, because they're all the scopes these days, from these manufacturers are all digitizing scopes or digital scopes, and we have to. There are two different types, if you will, of digital scopes. There's what we've been talking about thus far, which you can call as a digital real-time scope or single-shot scope, where the scope sample rate, we'll get into these topics, I'm sure, is much faster than the scope's bandwidth. So you can do a single-shot capture of waveforms and things like that. There's another class of digital scopes called sampling scopes or equivalent time sampling scopes that are, you might hear that term, and it's something that they're out there, and if you might find them used and things like that, but you may not understand what they're doing. What these sampling scopes will do is they often have very high bandwidth, but the sample rate is actually very low. And the way they work is they build up a waveform over multiple trigger events by essentially each time the scope receives a trigger, it delays ever so slightly where it's going to take the sample with respect to that trigger. So over time, it builds up the entire waveform on the screen. It requires that the signal is repetitive with respect to the trigger. And these are typically used in very high-speed applications like high-speed serial communications and things like that. And they're typically called sampling scopes. So when people talk about DSOs as a digital sampling scope or digital storage scope, I always want to try to clarify that, because in most cases we're going to be talking about scopes that sample at a very high sample rate, so we can do a single shot capture and emulate as close as possible the way an analog scope worked.
Well, and actually, the reason I'm asking this question, and George, feel free to add any color to this, there are, especially these days, as folks are working on digital circuitry, we've talked about a lot of analog waveforms, especially in radio, are repetitive, cyclical waveforms where you can actually look at the pattern and you're good. But with a lot of digital things, for instance, if you're working on an Arduino and you're doing something with, say, the SPI bus or the I2C bus, and there's going to be a single message that's a series of digital high-low signals, it's not going to be a repetitive thing. It's going to be a single event. And I know that on my scope, you can capture what happens over a period of time, and then I can jog the wheel and look for this single event. Do you have that ability to capture and look for single event type things on an analog scope?
Yeah, the way we did that in the old days was with a scope camera. So there was these Polaroid-backed cameras that would hang on the groove that's right above the CRT on the analog scopes. Cover that up, and you put a Polaroid film pack in there. Open up the little window to be sure you got everything set up on the scope. You close the window, open the trigger, set up your scope to trigger, capture your waveform. It would write it to the film. You'd yank the film out just like the old Polaroid cameras, and there was your single shot capture.
That's exactly like photographing lightning.
Yeah, so that there was that, and then there were a kind of a special class of analog scopes that were analog storage scopes, where the phosphor on the end of the CRT was biased such that once you wrote to it, it could retain that written image, so you could actually look at it and examine it. And usually over time it would kind of start to blur and fuzz and bloom, and then you had to clear the screen and do it again. So those were the two ways that we did that back before we had storage scopes.
I'm very thankful for digital storage scopes.
Yes. But yeah, and like you said, and that's that's a great decision point. If someone says, do I need an analog scope or a digital scope? If you're ever going to be working with Arduinos or PICs or things like that, and controlling displays and controlling other devices, and you might be using, I2C buses or SPI buses or even RS-232, and you need to look at those digital patterns, those digital messages, that basically says it right there. You really need an analog storage, or you need a storage scope, a digital scope.
I'd throw in there that it kind of depends on, do you want to go into a logic analyzer at that point? So there's sort of now with a digital scope, there's sort of a fine line between what's a scope and what's a logic analyzer. That's
a good question. The thing is, the logic analyzer will hide something from you, though, because all it's going to do is tell you ones and zeros, meaning above or below a decision threshold. If you have any distortion on those digital waveforms, like ringing due to reflections and noise, that might cause mistriggering on the logic. The logic analyzer might hide that from you, whereas a scope won't.
So the scope is really showing you the electrical signaling properties of that physical signal as opposed to the logical representation. So I guess from a practical point of view, you could either go with a digital scope where you get both the signal quality and some level of digital storage. And some of these digital scopes have those bus protocol decoders built in. So they actually represent, hex values or whatever of those bits versus an analog scope and a logic analyzer where you kind of go to the extremes and you have a tool that's like really for that particular thing. And while we're at it, let's take a quick pause for this message.
The Workbench is sponsored by our friends at CADsoft. They're the makers of the Eagle PCB design software, the very software George used to design the Pactena Classic, Pactena Mini, what him and Barrick are using to create this new antenna analyzer project for you here on the Workbench. They got hundreds of parts libraries, tons of reference designs, and a monster huge user community. Eagle's a great choice for your next ham radio project, and you can get your free copy of their software today. Click on over to cadsoft.io and start getting your project put together today.
Real quickly, for those who don't know what a logic analyzer is that in digital electronics, ones and zeros are represented by a high voltage state and a low voltage state, and it's not as easy as just, say plus 5 volts and 0 volts. There are thresholds that a 0 is usually under in a 5 volt circuit, a certain thing and whatnot. So a logic analyzer allows you to actually capture the virtual ones and zeros, but maybe not the actual voltage levels. And then for computer-based ones, there's usually a software package that will decode those things. So for instance, if you had a serial port and say a GPS, which this is one of the best demonstrations I've ever shown to somebody, a GPS will spit out serial NMEA data. I can hook that up to a logic analyzer, and my computer will take the digital signals and decode them into ASCII text, for instance. These days, there's another classification of device, and again, this is all based on measuring waves and then decoding them, called a mixed signal, either analyzer or oscilloscope. So there are oscilloscopes available that actually will have a logic analyzer built into them so that you can simultaneously get logic level readings and decoding along with the actual voltage traces. There's also, I have one by a company called Saley, which was, you can get them for like $100 or $200. The software is really nice. Same thing, it's a mixed signal scope, so I can capture both the digital signals with the decoding, but also connect to the same points and capture the analog oscilloscope traces digitally.
Yeah, and another thing to think about too is that a lot of these oscilloscopes, even if they're mixed signal scopes or not, even some of the analog scopes allow you to look at these, some of these serial buses that don't use a lot of pins and actually do the decoding even off of the analog channels. I know that the tech mixed signal scopes allow you to define a bus using both the analog and digital inputs. But beyond just doing the protocol decode and showing you the messages, oftentimes these same scopes can do that decoding live so that could become one of your trigger events. So you can set up the scope to trigger each time your I2C bus spits out this address. So that you can see how your hardware is reacting to a particular address or a particular word or a particular command that is being sent over the digital bus. Now
we've gone super deep advanced, and I know we may have lost some people at this point, but for those who are interested in this, I mean, the scope that I have, which is a Regal DS 1104ZS, there's actually software options you can purchase to unlock both protocol triggering, where based on a certain serial RS-232 event or an SPI or an I2C event, you can have it. That's where the scope will start recording. And then also it will do protocol decoding. But I will tell you, I have these features on my scope, and I have really struggled to get them work, which is why I ended up buying a dedicated computer-based signal analyzer. But then again, my scope was under $1,000. Alan, I'm sure you have access to all the wonderful $40,000 and $60,000 scopes that Tech makes.
Even up to the $300,000 scopes that Tech makes.
I don't want to talk about scopes that cost more than my house. Our listeners.
Actually, while we're on that, actually, I've got a question for you. So, what in the world would make an oscilloscope $300,000?
Well, we've got kind of the top end of things where the analog bandwidth of the scope is gigahertz. So sample rate of 200 gigasample per second. These are scopes that cost $300,000, types of numbers. So people that are doing super high speed, coherent optical communications and ultra wideband radar systems and things like that need that level of performance. So
well, that's exactly what I got on my workbench this week is some ultra wideband optical communication stuff. That's what I'm totally working on.
Okay.
I know where you can get an oscilloscope if you're in the market.
Yeah, well, I tell you what, it better be big enough that I can park 2 cars in it and put a swing set behind it.
Yeah, right.
Now, this is actually a perfect segue because one of the things that even to this day, I still don't even understand this concept is the concept of scope bandwidth. This is probably one of the most important specs you will look at when evaluating oscilloscopes. For instance, the scope I have is 100 megahertz of bandwidth oscilloscope, but I really don't know what that means. So why don't you two shed some light on what is scope bandwidth mean, and how much scope does the average ham need in their shack?
Yeah, more great questions. So think about, like, even going back to the analog scopes. If we put a varying AC signal into, say, channel 1, and we're going to visualize and see that waveform, on the screen, the processing of that waveform from your probe, goes through a preamp and then some, vertical drivers that drive the vertical deflection plates on a scope, or in the digital scope, it has to go through some scaling circuits and some amplifiers to go into the front end of a analog to digital converter. Just like any type of amplifier, any circuit is only going to respond up to a certain frequency. At higher frequencies, it's just not going to have the response. And that's really what we talk about when we talk about bandwidth. More specifically, if we say a scope has 100 megahertz of bandwidth, it doesn't mean that the scope won't show you something that's 101 megahertz, okay? But it also means that if you put in a signal that is 100 megahertz, it is not going to be at full amplitude. The scope bandwidth is the 3 dB bandwidth of the vertical channel, which means that at low frequencies, the scope is going to show you exactly what the true amplitude of the signal is. And just like any other circuit whose bandwidth starts to fall off at high frequency, the response of that amplifier, or the response of the vertical channel of the scope, will begin to fall off as the frequency goes up. And the bandwidth rating of the scope is saying that we're guaranteeing that at that rated bandwidth, your signal will be 3 dB down from its real amplitude or larger. So it means that it's not going to be anything more than 3 dB down. Okay. So if you're looking at a 100 megahertz signal on a 100 megahertz scope, it could be somewhere between 100% of its real value, or maybe as far down as 70% of its real value. And I actually did a pretty good video on scope bandwidth, kind of showing what it means. Like, even my 35-year-old 465B 100 megahertz scope, it's rated at 100 megahertz, but it's 3 dB down at about 120 megahertz. It's not quite 3 dB down, so it's attenuated, but it's not down as far as the 3 dB value. It's only about 75 or 80% down at 100 megahertz. So does it mean that you can't look at a signal that is beyond the bandwidth of the scope? No, it doesn't mean that at all. But it does mean that the signal may not be at the real amplitude of what the signal is. So it's kind of a soft bandwidth limit. Go ahead.
So I think when you're shopping for scopes, one of the first things you run into is this bandwidth or highest sample frequency. Because as that number goes up, like you're saying, the $300,000 scope, one of the reasons it's that expensive is because of that incredibly high sample rate. Yep. So for us hams, when we look at a scope, the scope ratings are typically going to be things like 10, 20, 50, 100, 200, 400 megahertz. And if you're doing audio, the lowest frequency scope you'll ever find in a normal commercial scope is like 10 or 20 megahertz. And even those are harder to find these days. And that's way above anything you'd ever see in the audio domain. So if you're doing audio work, pretty much any scope would be okay in terms of frequency response.
It will.
Would you say?
Yeah, it will, and that's a great question or a great comment. And people think, oh, I don't need a 100 megahertz scope or a 350 megahertz scope. I'm just doing audio work. The thing you do have to remember, though, is that sometimes if you don't have enough bandwidth, things can hide from you. It's not too uncommon for, a single transistor audio amplifier, if it's not set up right, to oscillate at 300 megahertz. Okay. And you may not see that if you looked at it with a 20 megahertz scope. Okay.
So we had a little project we were working on. We built a repeater controller, and all of the audio paths, a very inexpensive, in fact, it was a used Tektronix oscilloscope that we bought at a swap meet for like $100. And that was perfectly fine, but we had a problem on the back plane because there was an I2C channel, and it wasn't working right. And so we had to look at that, and we were looking at not only the clock rate, we were looking at ringing on that back plane, and the harmonics of this square wave. We really had to have a higher frequency scope to see that stuff. So that extra headroom, you're right, it really can be very handy.
Yeah, like I said, if you're talking about analog circuits and RF circuits and IF circuits, it's pretty easy to say, well, hey, if I'm working on an HF radio and I want to see the HF output, I'm going to need at least 30 megahertz of bandwidth. Okay, if you want to actually look at the RF signal itself. If you're working on VHF and UHF things and you actually want to see the RF signal, then that means a higher bandwidth. Things get a little fuzzier and harder when you start thinking about digital signals, because you might say, well, my clock rate in my circuit is 10 megahertz, so I don't need a real fast scope. But that's a 10 megahertz square wave. And so exactly. You brought up a great point, George, that a 10 megahertz square wave has got energy at 10 megahertz and 30 megahertz and 50 megahertz and 70 megahertz, all the odd harmonics. In fact, what really drives how many of those harmonics are there is the rise and fall time. How quickly does that signal go from logic 0 to logic 1? If it rises up in a nanosecond, okay, you're going to need a 300 plus megahertz bandwidth scope to see that. Okay, So, well, it's a 10 megahertz signal. Yeah, but it's got a rise time of a nanosecond. If you don't have the bandwidth to see that fast rise time, because you have to think about it, at the end of the day, it's a low-pass filter. So if you try to put a fast signal through a low-pass filter, it's going to make it slower, because it rolls off those higher-order harmonics. So, you almost have to think, well, your good rule of thumb is you probably want your digital scope bandwidth, or excuse me, your scope bandwidth to be probably 5 to 10 times the highest clock frequency that you're dealing with in your digital circuits.
So that's a great piece of advice. Let's map that back to, let's say the guy who wants to set up his bench is going to go get his first scope. So if he's going to go get the $50 special at the swap meet, it doesn't matter if he gets the right thing or not. But if he's going to go buy a brand new scope from the test equipment company, then how fast of a scope would you recommend? Now, of course, the answer is, well, it depends on what you're going to do with it. But if you really don't know yet, but you still want a scope because, you really want that visibility, what would you recommend?
Well, I mean, what I usually tell people is if they don't have an idea, get as much bandwidth as you can afford, because you'll probably wind up using it eventually. Okay. Another way to think about it, kind of the old analog rule of thumb for scope bandwidth. If you're thinking about digital circuits, you want to think about the scope's rise time. Sometimes the scope has a spec for rise time. How fast can the waveform, what's the fastest rise time you can see, or what's the inherent rise time of the scope? The old rule of thumb was a factor called 0.35 divided by the rise time. So 0.35 divided by the rise time would tell you roughly what the analog bandwidth of the scope is. Okay, so a 3.5 nanosecond rise time is a 100 megahertz scope. Okay, so this is probably the more and for some of the digital scopes, the rule doesn't exactly apply, but it's close enough to give you an idea. So well, do you know what the rise time of the logic circuits you're looking at are? Probably not. So then again, you might want to say, what's the fastest signals I'm going to be looking at? What's the clock rate of my processor or whatever I'm dealing with? Then go 5 to 10 times that. So, today, I think I would recommend people, 100 megahertz as a bare minimum. There may be instances where you need more than that. For the average hobbyist, probably not that often. I most of the time when I'm working on my bench, I rarely need more than 100 megahertz worth of bandwidth because truthfully, once you get above that and you really want to see signals with that level of, frequency content, you do have to be really careful when it comes to probing and things like that, which is whole nother topic we could talk about. So a 100 megahertz scope will serve 95% or more of the average hobbyist.
And what kind of...
Well, hold on. That's good, because that means I bought the right amount of scope for me for right now.
Sure.
Price-wise, I'm sure it depends on the vendor and all that stuff. But if you go out to buy a scope, let's say a good 100 megahertz scope, they seem like they're in the $400 or $500 range, kind of brand new if you're not shopping too much.
Yeah, I think, like I said, Jeremy, I know you said you've got the Regal scope. There's a lot of what we call inexpensive, digital scopes out there, especially coming out of China. And of all of those brands, probably the Regals are probably the ones that I would probably trust the most out of those inexpensive, kind of the non-professional brands, I'll call them that. And really not too bad for the hobbyists. There are, really nice scope for the hobbyists. Some of the major manufacturers are also providing lower cost scopes. What you'll find is that dollar for dollar, feature for feature, some of the, like a Regal type brand would probably offer you more capability for the same money versus, a Tektronix scope for something for the same amount of money. That's just, there's a lot of reasons for that. We can, it's a whole other topic, but it gets into the components used and reliability and all these types of other things, signal integrity. But for the average hobbyist, these Regals and things like that work really well.
Now, I'm sorry, go ahead.
No, go ahead.
I was going to say, I'll add the color that, because again, when I was a kid, an oscilloscope was something I wanted. As I got older, I got to be an adult. For the same reason I decided to be a ham is because I was like, hey, I have an income. I'm an adult. I can do this now. As I was buying up test equipment, it was actually Dave Jones on the EEV blog that made me aware that you could buy a modern scope. And at the time, it was a 100 megahertz scope for $400. That was the Regal DS. I think it was the 1102 Echo.
Right.
And, it was a digital storage oscilloscope. It had a small little 640 by 480 display on it, but there were so many features and so many things. And more importantly, it was a 100 megahertz scope that was new for $400. And
with a warranty and everything.
Yeah. And from honestly, one of the, Regal, as far as, because there's a lot of these Chinese manufacturers that have popped up. There's Owan, there's Siglent, and then there's a bunch of other ones that I won't even mention because God forbid you wind up buying one of their scopes. But Regal had a pedigree, as in they used to manufacture the low end stuff for Agilent. That's where they got their start.
Yep.
And for them to be able to bring that, I mean, it's just like eye opening is not the right word, but it is a gateway for the hobbyist to get a lot of capability. And of course, the average guy at home on their bench like me, I don't need a NIST certified, precision scope. And in our last episode, we really talked about test equipment as indicators versus instruments of precision. And the average ham really needs an indicator. They're not trying to track down a gigahertz, some type of a glitch on a board they've designed that only happens 1 out of 1,000 test runs.
Right, exactly. And like I said, like these Regal scopes, again, really great bang for the buck for folks that want to get in on a digital scope. And I guess if I was going to go that route, I'd probably go Regal instead of some of these other, kind of third party brands, simply because they've been out there long enough and they've you're less likely to find glitches and bugs and problems in them than you will with some of the other brands. And
when they do, there's a really active community around these, especially on the EEV blog forum, which we'll post a link to. And what's nice is they actually issue firmware updates. They actually have a support and sales office here in Ohio. I mean, they have an American presence. In fact, they come to Dayton.
Right.
So as far as buying new goes, that's great. Now, here in a little bit, we'll talk about buying used. Because again, after talking to you, I'm starting to wonder if there's actually room for an older analog scope on my bench, just as a different type of instrument. But
yes, by the way, the answer is yes to that question. I'd be happy to ship you one of mine.
Actually, what's funny is the University of Cincinnati had one of their quarterly surplus meetings. My brother-in-law was like, oh, you like electronics? Here is a pallet of oscilloscopes. And they're all the old 1940s and 50s styles with the big round display in a box that's approximately 3 feet tall. And of course, all of them came on carts, which some other ham friends of mine say it's not test equipment if it's not mounted on a cart.
And it doesn't glow.
Yeah. That is one thing. You can't warm your workbench or your workshop with digital scopes these days.
Right, that's true.
Now, we've talked about bandwidth, which is again, probably the first spec that you run into. Now, the next thing is channels. And of course, what channels are is how many signals can you display simultaneously, correct?
Yes.
Okay.
So, and most of the scopes, even the entry-level scopes, are going to be a minimum of 2 channels. And again, probably for 90% of those applications where you're just a hobbyist and you're visualizing waveforms, 2 channels is often all you need. Most of the time, you're just using 1. You might bring up a second channel if you want to look simultaneously at the input and output of a circuit to make sure the circuit is doing what it's supposed to that signal. Or if you have a different signal you want to synchronize or trigger against to look at, a given signal. So 2 channels is the bare minimum. There are instances where more than 2, like 4 analog channels, can be handy because you might look at, how are these 3 waveforms reacting in response to this trigger event that I'm looking at on channel 4. Those kind of things don't happen that often, but there are situations the more you get into design and debug that could be handy. But I would say 90% of the time, 1 channel is good enough. 95% of the time, 2 channels will get you there, and the last 5% is split between the 3 and 4 channels if we're just talking about analog channels. But if we talk about the mixed signal scopes that we mentioned earlier, oftentimes they'll have 8 or 16 digital inputs as well. One thing you've got to be careful of is that the majority of the mixed signal scopes that are out there, if they've got an 8-channel digital input, they often will let you adjust the threshold, the logic threshold, to determine what voltage level determines a 1 or a 0, whether you're looking at low-power CMOS circuits or TTL circuits or whatever. But they'll oftentimes adjust that logic threshold on all 8 of those inputs at the same time. So you have to be a little bit careful with that. There are mixed signal scopes out there that allow you to adjust that logic threshold independently on each of the digital inputs, but that's not the majority. That's a bit more the minority.
And another feature that I have seen is that while some of them may give you 8 or 16 channels, the more channels you activate, the lower your bandwidth per channel becomes, or your sample rate per channel.
On the analog channels, that's true. Oftentimes the digitizer and oftentimes the memory is shared. So that you might get a gigasample per second on 1 channel, but 500 megasample per second on 2 and 250 megasample per second on 4. That's very common, and it's just again just manufacturers figuring again for the same reason that hey, most of the time these guys are using 1 or 2 channels. Why not interleave these digitizers to give the user a higher sample rate? So that's really what that comes down to. But so you do have to think about. And you have to be careful too to be sure that if you buy a 4-channel analog scope that's rated at 100 megahertz, is it 4 channels at 100 megahertz simultaneously, or is it only 100 megahertz when 1 channel is activated and you're something less when you have two or more channels activated?
And I think that's pretty common in the lower when we talk about what's the difference between a $300 scope and a $3,000 scope. I think that's the sort of thing you would see as a difference. I know on my scope, which is 100 megs, I'm pretty sure it divides down because there's only one big ADC, analog to digital converter, and it's going to be multiplexing between multiple inputs as a way of saving costs and not having to have 2 or 4 of those things inside.
Sure. And on the other hand, if the sample rate divides down, as long as the divided down sample rate on multiple channels still supports the rated bandwidth of the scope. I mean, if it's a 100 megahertz scope and it's doing 250 megasample per second, that's just barely enough, okay, just above Nyquist to support 100 megahertz on all 4 of those channels. So even though the sample rate is lower, you're still getting the bandwidth that you paid for.
So obviously this concept of sample rate is something unique to a digital scope. So, for instance, the Regal that I have, when, like you said, it's exactly like that. With 1 channel active, it's 1 gigasample per second. If you do 2 channels, it divides in half. If you do all 4 channels, it's 250 mega samples per second. What does that sample rate actually mean? Like, what does that get you? Why does that matter as I'm shopping for scopes?
Okay, so think of sample rate as, how quickly does the scope take a snapshot of the amplitude? Okay, so if I had a 100 megahertz signal and I was sampling it at 2.5 gigasample or at 2.5 megasample per second. That means for every cycle, every single sinusoidal cycle of that 100 megahertz signal, I'm only taking a picture of the voltage 2.5 times. So I've only got 2.5 sample points to represent that sine wave. So how accurately do you think you can represent a sine wave if you only pick out two or three voltage points on that sine wave? Versus if you're oversampling the signal by 10 times the frequency. Right? If you're looking at a 100 megahertz signal, sampling at a gigasample per second, you'd have 10 points, 10 sample values in memory. So the more you can oversample the signal, the more accurately you can represent that signal.
All right, so it's basically resolution of the sample capture.
Yes, it's the finest resolution of sample points in the waveform over time, basically horizontally.
Well, okay, so for those of us familiar with like computer audio capture, I mean, I guess I never realized that that's exactly what that is, right? The sample rate of say a 44 kilohertz wave file, same thing, is it is taking 44.1 44,100 samples per second of those waveforms, and that's basically drawing that's resolute enough to create analog audio that we can all listen to and enjoy. So that makes sense.
Yep, that's exactly right. And that's 44.1. It's figure audio, high fidelity audio, people can hear up to typically 15 to 20 kilohertz. So it's oversampling that by a little more than 2x. Okay, and at the very least, you've got to be twice the highest frequency content of a signal. That's called the Nyquist criteria. Because what happens if you don't meet that Nyquist criteria? Think about the old westerns on TV. You're watching the old western movies, and sometimes it looks like the wagon wheels are going backwards.
Yes.
Okay?
Yeah.
Okay. And that is something called aliasing. That means that the sample rate or the frame rate of the video was not quite fast enough to accurately capture the rotation of these wheels. So it might be undersampling that, so that the samples that it does grab actually are just, and you put those pictures in succession, it happened to grab pictures of the wheel in slightly different positions that make it look like the wheel is going in the wrong direction or traveling slow. That's called undersampling and aliasing. The same thing can happen in digital scopes if you undersample a signal. And the other thing you have to watch and be careful of is with the analog scopes, they can alias even if you have enough sample rate. The scope is rated for enough sample rate. What I mean by that is the sample rate of the oscilloscope has implications on how much memory is used. If I've dialed the horizontal scale down to something slow like a millisecond of division or 10 milliseconds of division, and the scope can capture at a gigasample per second, you'd need a ton of memory to fill the screen, right? Because if you're doing a second or a sample every nanosecond, and you've got 10 milliseconds between division points, you're going to have thousands and thousands of points just between the divisions. So you need a ton of memory. So the scopes will typically not have that much memory, or they might not be set to that much memory. So in effect, what the scope does is it reduces the sample rate when you go to lower horizontal scales, or to, I should say, longer horizontal scales, like a millisecond per division or 10 millisecond division. So the scope sample, the effective waveform sample rate goes down. So if you're looking at an RF signal and you've got your horizontal time base set too slow, the effective sample rate of the waveform won't be your 1 gigasample per second or 250 megasample per second. It might be something much less. And then those samples could undersample your RF signal and show you something that isn't real. Okay, it'll actually alias the waveform,
like the wheels turning backwards.
Like the wheels turning backwards, and you might find that if you experiment with putting like a 10 megahertz signal or a 100 megahertz signal in your scope, and then start dialing the horizontal time base down slower and slower, eventually the whole waveform turns into a big fat band because you can't resolve the cycles. If you keep going lower, all of a sudden you get a sine wave again at a much lower rate, and it's not synchronized, just moving back and forth. That's aliasing the signal. And it's lying to you.
For the 2x oversample, that's really only useful for measuring the frequency of the signal. It doesn't do you any good to give you an accurate understanding of the wave shape.
Absolutely right.
So that's really where the sample rate versus the frequency, you really have to look at your application. Are you just trying to frequency measure, or are you trying to really look at is it a sine wave or not?
Yeah, because if you sample it exactly 2x, okay, it all depends on where those samples are lined up with respect to your signal. Because if you think about a sine wave, it crosses through 0, as it's coming up, going down as it comes back up again. If you sample it exactly 2x at exactly the 0 crossing points, you don't measure anything, right? So every sample point would be 0. Even if you were lucky and you sampled at the positive peak and the negative peak and the positive peak and then a negative peak, all you have is those 2 points. You don't really know. You know what the frequency is. You can't really tell what the amplitude is because you don't know where those points lie. So that's why the Nyquist criteria, like you said, is only to kind of establish at what point am I going to be undersampling the signal and potentially aliasing the signal, where the signal could look like something completely different in frequency than it really is. Once you're above Nyquist, you won't alias, but your amplitude may not be as accurate. So the general rule of thumb that people are using, or that they might want to think about, is that at the very bare minimum, you want to oversample by at least 2.5x. Okay, at least 2.5 times the highest frequency content you want to look at. And that's where I get down, like the Regal at 4 channels at 100 megahertz, it's sampling at 250 megasample per second. That's why I made the comment that that's that's just barely enough. You wouldn't want to go any lower than that.
Okay. We talk about these measurements, and we're starting to get more into the content around digital scopes than analog scopes because, again, this whole concept and conversation around sampling rates is specific to digital. We on the analog side, because I think we're about to mostly bid them adieu, although I look forward to being proven wrong here shortly, as usually happens. Are there any other features other than just displaying the waveform, adjusting the horizontal and vertical scales? Are there anything else that analog scopes can actually do with that wave? I'm calling it data, but it's not. It's just signal displaying. Because I know we're going to talk here in a minute about digital scopes can do all kinds of functions and math and show you measurements on the screen. What about analog scopes? Well,
I think there are 2 areas where analog scopes in most cases still do a better job than the digital scopes today. Okay, one is one that I mentioned earlier, and that's using it as a monitor for, like, if you want to monitor your RF output, like an old station monitor. And I've got an old Kenwood station monitor, SM230 here that I use on my, or SM220 that I use on my station here, but I've also used analog scopes in the past. So that's where we're looking at the modulated RF envelope. The horizontal time base is set such that I'm looking at about a millisecond of division. On most analog scopes, that works just fine. So that the RF is moving fast enough that you can't resolve the sinusoid of the RF signal, but you can see the envelope of it to see how it's being modulated by your audio. The analog scopes do that very naturally and really very, very well because it's a analog persistence display. Now, the digital scopes will often have trouble with that because as you dial the horizontal scale down to low enough to see the audio envelope, the sample rate of that waveform is going to be low. And oftentimes it might be too low and it will undersample the RF and won't do a good job. On some scopes, you can adjust that, say, okay, use more memory so I can crank the sample rate up, but now the response time of that scope goes down. So since you've got a Regal, it might be interesting to look at that, Jeremy, to see, can I really get a good picture of what my RF envelope looks like if on a single sideband signal? Okay, just make a little RF tap and tap into your RF output and see if you can actually see that. That's something an analog scope can do very easily. So that's one application area that from a ham radio standpoint, an analog scope is actually usually better than a digital scope. And to some extent, it doesn't matter how much money you spend to do that because even some of the better digital scopes don't do a good job with that. Another application area is a whole myriad of what I call XY applications, okay, like Lissajous patterns, where if you want to make like a homebrew curve tracer, there's a lot of applications where if you want to drive both the X and the Y axes from external voltages rather than to let the scope drive horizontally. By being able to move the beam in X and Y in response to 2 different voltages, there are many applications where that can be pretty useful. One application that's often used in radio applications is if you're maybe using a sweep generator to sweep an IF filter or something like that, and you want to peak and align a tuned IF stage. You can drive the X with the sweep voltage that's driving the frequency change of the sweep generator, and then drive vertically with the output of the IF. So you can make your own kind of pseudo spectrum analyzer by doing things like that. So these types of tips and tricks and things that were done with analog scopes back in the day, some of these are still done better by the analog scopes than the digital scopes today.
I'll give you one more to throw on the pile, which is really not a technical thing. It's an aesthetic thing. And that is, if you're doing a lot of audio work on an analog oscilloscope, if you have a pure sine wave, it's a pure sine wave. When you look at that on a digital scope, you get this sort of pixelated version of a sine wave, which still irritates me because it doesn't look the way it should. Even on a pretty good digital scope, maybe a very expensive one, it's fine. But on the garden variety $300-400 scopes.
Yeah, well, and part of that is because the scope is, because it's a sampling scope, it's going to show you all the samples. So it's going to show you the noise. On an analog scope, things that occur infrequently, like little noise peaks and just the peak-to-peak excursions of noise, are not going to be as bright on a CRT, because most of the time you're looking at an analog scope, you're looking at a spot where the beam is written thousands and thousands of times a second in the same spot. So it effectively is a bit of a noise filter, whereas a digital scope, all the values are all the values. They all just happen. So it looks noisier and fatter on the analog digital scopes than it does on the analog scopes.
So sometimes it's better to live in that fantasy world of my audio is perfect on my
there you
analog
go. Yeah, there's no noise on this. It looks great.
It's awesome.
If it doesn't look great, turn the intensity down a little bit. It'll look great then.
It'll look even better.
Right.
Another thing that's interesting is on digital scopes. I mean, you're at least on the low end ones, you're outputting to whatever the LCD is in there. In the case of my scope, for instance, I was just trying to look this up, but it's like 700 pixels by 400 some pixels. And at the end of the day, a lot of the actual data points that would draw these lines, they're far more resolute than what the physical screen is able to show. Now, granted, on my scopes, you can zoom in, but it's almost like the actual LCD display on the scope acts as another filter on the data set before you actually look at it.
It is. Oh, go ahead, George. Go ahead, George.
No, I'd say that's kind of my point was like, just because it has to get dumbed down to the resolution of the pixel array on the display, you kind of wind up with more stair steps than maybe are even there. So I totally appreciate the point about you might actually see real artifacts that are really there. And then there's also the artifact that you see of the pixelization in the display.
Yeah, there's the other thing too is, another application area, a bit more esoteric, but allows you to get pretty creative about what you can do with an analog scope, is a lot of them allow you to modulate the z-axis or the intensity of the beam. So there, you might say, okay, I want to look at this waveform, but I want to intensify it in certain areas or certain, based on certain other signals. You can actually have a third input, usually on the back of the scope, to modulate the intensity. In fact, anybody who's looked at my YouTube channel for the first time sees an introductory video of me talking about what the channel's about, and it looks like I'm actually trapped inside my oscilloscope. What I actually did is built a circuit that takes NTSC composite video and turned it into the X, Y, and Z voltages that would be needed to turn my scope into an analog video monitor. And I've just had my camera pointed at my old 485 scope as a video monitor. And so, in fact, I don't know, on Skype, my little avatar might actually be a picture of that too.
It is,
yeah. So that quite literally is what appeared on my 485 scope screen through this circuit. So you can do interesting things if you start thinking about modulating the z-axis as well. It isn't an everyday application, but boy, you can do some really creative things that where, with the digital scope, the things are a bit black and white. There's a lot of things it can do in that two-dimensional space, but in an analog scope, you almost have that third dimension that, of the analog persistence of the trace, as well as the ability to potentially modulate that analog intensity.
To channel Cale for a minute, George, I'm really glad I know smart people.
Well, and I'm really glad this is recorded because after you listen to it, you can go back and listen to it 4 more times till you get it.
Yeah. Well, again, that's one of the beautiful parts about having all this wealth of additional video material. This will be the first episode that we have that's going to have homework.
There you go.
Now, normally we would we kind of save recommendations towards the end, but since I think that going forward we are going to kind of start talking about features that are more specific to digital scopes. What are your guys' say top 3 recommendations for used analog scopes that you would recommend somebody pick up?
In terms of brand, or what do you think?
I mean, brands and models, and
Okay.
maybe you're looking in that $50 to $100 range, and then maybe the 101 to 250, and then up to $500, or maybe that's not even the right way to do it. But I mean, features versus price versus stuff that's not going to break the bank, but is a good starting point. You guys tell me why you're picking them.
Okay, George, why don't you go first?
Oh, okay. I guess I would look at 2 things, and that is, do I want to spend as little money as possible to get something pretty good? And then the second decision would be, do I want to spend a bit more money on a brand new thing? What would it be? So I think for a relatively inexpensive scope with good bang for the buck, I would get a used Tektronix or HP scope. I think in a way, Tektronix, probably there's more of them out there than anything. And unless there's something wrong with that particular unit, you really can't go wrong, because a cheap branded analog scope is, maybe good, maybe not. But if you find a good Tektronix used scope for $100 or $200, it's pretty hard to beat. So I would certainly look for that.
Do you have any specific model numbers? Because, I mean, this is one of the issues. It's like buying Motorola radios at Hamfest. I actually saw a guy once go out and buy a Motorola radio. He spent like $600 on it. He was very proud of himself. And when he got it home, he realized it can only talk in the 800 megahertz range. So,
and it was probably called UHF. So, I've got 2 old analog tech scopes on the bench, and I really do need to go look at the model numbers. But I think I want to say 465, but Alan, you really know this better than I do. Does that sound right?
Yeah, it could be. I mean, like I said, the 465 was the most popular 2-channel analog scope that Tech made back in the 70s. Look at your budget and see what you can find out there for the analog scopes. You certainly, like you say, can't go wrong sticking with name brands, Tektronix and HP. Some of the other kind of second-tier brands like Hameg, Leader, Kenwood, Hitachi, they made nice quality scopes as well, so you couldn't go wrong there. Something I'll state too is that what I would call service grade scopes, and some of the older service grade scopes were actually something called recurrent sweep scopes, and they didn't have a trigger. They basically you didn't set the time base in a calibrated way. You set it in frequency. Like, I want to move that beam, at a kilohertz or 10 kilohertz or something like that. And they had like a sync control. It really was just a visualization tool. And those were the inexpensive scopes of the days, and they typically found their way into service markets like TV shops and things like that. In this day and age, there's absolutely no excuse to buy a service grade scope. There are so many professional lab grade analog scopes out there that are true triggered scopes. They have trigger controls on them, calibrated horizontal time bases. That's what you want to get. In terms of specific models, you can look at them physically in terms of their size. You can decide whether or not you really want to go something that's old vacuum tube, but you probably don't. Want to stay away from them these days. They're hard to find the tubes for. Like I said, the 465 or 465B, really great 2-channel analog scopes. The next scope in that family up, the 400 series family scope, was the 475, and that was a 250 megahertz, 200 to 250 megahertz scope. Not quite as popular, but the same physical size, very reliable. There was a 485, which is a really nice scope, a little bit harder to come by. It was actually the first 350 megahertz scope that would fit underneath an airline seat. That's one of its claims to fame. But really nice scope with a super sharp display on it. Those were all late 70s, early 80s vintage scopes. So they are, even though the scopes are very reliable, you're getting to the point where some of the plastic components start to get brittle. Okay, so even though the scope is great, the plastic feet on them broke off, or maybe a knob is cracked or something like that. So you really want to kind of see it, play with it, adjust the knobs, switches, make sure they all work. Moving up a generation on the Tektronix side, 'cause that's what I'm most familiar with, is any of the 2000 series scopes, like a 2200 series, like a 2215 or things like that. Great scopes. Those are pretty inexpensive even when they were new. They're still good scopes today. 2200, 2225 was a little bit wider bandwidth. I think a 2215 was a 60 megahertz scope. The 2225, I think, was 100 or 150. The next level up were the 2400 series. Actually, it was a 2300, but then the more popular was the 2400 series scopes. A 2445 is a 150 megahertz scope. A 2465, very, very popular scope. 4 channels, 300, 350 megahertz. Very, very popular scopes out there.
So let me inject there. Just doing a quick eBay search just to give you some rough pricing. So the 465 and the 2000 series you started to mention, a bunch of those selling between $100 and $220. The 2400 series, there's a bunch for $200 to $300 used. So very good instruments for that price.
Yeah, absolutely. So those are, like I said, it's a nice way to get in if you don't really know what you're going to use a scope for, or you've got, maybe you just want a station monitor to start off with. Really nice way to go. And, by learning on an analog scope, you'll be more efficient in using a digital scope ultimately.
I would throw out one more thought too, which is those analog scopes have fewer things you can do with them. So when I look at my analog scope compared to my digital scope does a lot more stuff than I will probably ever use. And that could, especially for someone setting up their bench for the first time, that could just get in the way. It's not necessarily a plus to have a lot of features. You want a good set of basic features, not necessarily all that other stuff.
That's true. Yeah, 'cause sometimes you might get lost with
exactly
all the things it can do. Yeah,
that's right.
So one other, I guess the last question that I'll ask about analog scopes, especially since, at this point we're not recommending you buy modern new analog scopes. I mean, buy some of these classic, really high-end units. Alan, if I'm buying a used 465 or 2245, one of the other issues I have is I don't know how to test it. How do I know I'm getting a good unit that is close to calibration? Is there anything that I can do, pre-sales to kind of make sure I'm getting the best value for my money?
That's a great question. And what I'd recommend is, if the scope has a probe or is being sold with probes, connect the probe up to, it will typically be a probe compensation or calibrator output on the scope. And that's to properly compensate a 10x probe. But hook up to that and make sure you can see that square wave on the scope. Adjust the horizontal time base all the way to the slowest and all the way to the fastest to be sure that you get a sweep in every one of those positions, that you don't have a problem with the switch going forward. Adjust the vertical control when you're hooked up to the calibrator to be sure that the signal is indeed increasing in size or decreasing in size as you change that vertical scale. Make sure that there aren't any dead spots in that. Sometimes you'll find that the controls might be a little dirty, like the old analog volume controls on your old stereo, right? As you wiggle the knob, things might get a little jittery on the screen. Things are really dirty and not really stable, then the scope might need a bit of work. It might have been in a smoking environment, which could lead to corrosion issues and things like that. But checking each channel to be sure that you've got basic functionality, and the ability to at least see the probe compensation signal. And to be able to adjust that time base back and forth, and you got a trace everywhere. That if all of those things basically work, then you're probably in pretty good shape.
All right, well, that's good advice. Now, I think that's a really good segue to move into the topic of probes with oscilloscopes. And of course, these probes aren't just simple little pieces of metal that are, contacting a circuit all the way through. They're a lot more complex than that. For instance, Alan, you just mentioned something. You said a 10x probe. Again, I know my probes are 10x probes, but I don't know what that means. I don't know what's a quality probe. What do you look for in a probe? So why don't we take a few minutes and talk about probes?
Okay, certainly. And I'm glad we brought this up because it is a misunderstood topic, and it is something that's important to think about. Because like I said, unlike the probes that come with your digital multimeter, Scope probes are not simple wires that connect to your circuit. The majority of the probes that you're going to want to use every day are what are called 10x probes. And the main reason is to minimize loading on the circuit, right? You don't want the effect of touching your probe down to your circuit to change your circuit's performance. Okay? So because we're talking about signals that can be, higher in bandwidth than your digital multimeter can see, things like capacitance of the probe that you're using can start to become important to think about. So, for example, if you look on any analog or digital scope, right next to the input connectors, it'll usually tell you that the input impedance is, say, 1 megohms in parallel with, say, 15 picofarads or 20 picofarads, because that's what the input loading is, what the input impedance is of that scope. Now, if you simply connected up 2 wires to that, okay, the wires are going to be unshielded, so they could pick up all kinds of stray signals from the air in addition to what you're trying to measure. So you don't want to do that. So you say, okay, I'll use coax because coax is shielded, and the connector is usually a BNC connector. It's got coax cable. Why don't I just, hook up coax? So at the other end of it, I'll just connect both ends of the coax, the shield and the center contact to my signal, and I'll be good. But you got to figure 50 ohm coax is going to have 20 picofarads per foot of capacitance. So by the time you take that piece of coax that's a couple of feet long and the scope input, that's might be 100, 120 picofarads. Now, how well is your circuit that's operating at 10 megahertz going to react to 120 picofarads being placed in that circuit where there wasn't one before? Okay, so that can really affect things. It also can low pass filter the signal, can low pass filter the things that look like you've got, this large capacitor you're laying there. So what 10x probes are is essentially at the end of a piece of coax, it's got a 9 megohm resistor in series between the center contact and the probe tip. So that 9 megohm resistor combined with the 1 megohm that's in the scope makes a 10x voltage divider, so that it does 2 things. One is that when you touch that probe to your circuit, the circuit doesn't see the 120 picofarads through the coax to the scope. It sees 9 megohms in series with that. So that effect of that capacitance is dramatically reduced. So the circuit doesn't get loaded so much, which is good. Your circuit performance doesn't change. The price you pay for that is that the signal that appears at the scope input is 10 times lower than the actual signal. That's where the 10x comes from. So the 10x isn't an amplification, it's a 10x attenuation of the signal. That's why it's called a 10x probe. And so you usually have to tell the scope, or some scopes will automatically sense a 10x probe, but most of the time for the inexpensive scopes, you've got to tell it you're using a 10x probe. So it will adjust its vertical scale to compensate for that 10x voltage reduction. Okay, but again, you're doing that to minimize loading. So when do you want to use a 1x probe? If you're dealing with very low frequency circuits, audio circuits, and really only when they're low impedance circuits where they can tolerate 100 picofarads or more of loading, can you use a 1x probe. So oftentimes the 1x probes are limited to a few megahertz at most in terms of bandwidth, where you can get 10x probes that'll go up to several hundred megahertz because of that. So what makes a good probe? Or if I buy a scope that didn't come with probes, what probes do I buy? Again, if you're just using the scope like most of us are as an indicator, okay, you just want to get scopes that are probes that are going to be durable and that they can be properly compensated for your scope. So what do I mean by that? I mentioned earlier that most of these scopes have a probe compensation or probe calibrator signal. And what that's there for is to set what's called the compensation of the scope probe. Because, in an ideal sense, the probe just looks like this resistor voltage divider, right? 9 megohms and, the 1 megohm input of the scope. It's just a 10x voltage divider. The reality is that, the scope also has that 10 or 15 or 20 picofarads of capacitance in parallel with that 10 megohm, or excuse me, with the 1 megohm that's in the scope. So once you get above a couple tens or hundreds of kilohertz, that 10 or 15 picofarads has a lower impedance than the 1 megohm. So the 9 meg resistor and this input capacitance is going to make a simple RC low pass filter. And all of a sudden that 10x voltage divider doesn't work anymore. So what they do in the probes is they intentionally put a capacitor around the 9 megohm series resistor, so that at very low frequencies, the 10x voltage divider is a result of the two resistors. As the frequency goes up, the 10x voltage division ratio still happens, but now it's dominated by the capacitors and not by the resistors. And since the input capacitance of all these scopes can vary, the probe manufacturers make the capacitor that's built into the probe adjustable, so that you can make the probe's capacitance around that 9 megohm resistor be exactly a ratio of 10 to the input capacitance of the scope. So that now at high frequencies, the capacitive voltage divider effect is also 10x. And then the way you do that is you hook the scope up to that probe compensator, and you literally physically adjust the little trim cap inside the probe until the square wave looks perfectly square. It's as simple as that. But that's a 2-minute discussion on 10x probes. I did a couple of videos on that too. But the bottom line is, if I just got a scope, I need to buy probes. My scope says it's got a 20 picofarad input capacitance. When you're shopping for probes, make sure the probes are rated for the frequency of the scope or greater, and that the compensation range of the probe contains or will encompass the input voltage or input capacitance of the scope that you're dealing with. So if I've got a 20 picofarad input capacitance of the scope, I find a probe that says the compensation range is 15 to 30 picofarads, that will work.
Well, okay. Probes.
Okay, so I dive deep into that thing because it's something it's something that's often misunderstood, and so many people, oh yeah, I got that little screwdriver that came with my probe, I never used it, because they never compensated your probes, and it can be really important. The errors once you get up above 10 or 20 or 30 kilohertz can be significant. You can be measuring voltages that are twice as big as they should be, or half the size as they should be, if you're not properly compensated.
So, if you go out and buy a new, say, Regal scope, I mean, I got 400, actually, I think they're rated at 150 megahertz in their 10X probes. And as an example, if I were to buy them new, I think they're like $30 a piece. Do you have any guidelines on buying separate probes, or if somebody does buy an inexpensive scope, does it make sense to go out and buy like a nice set of Tektronix probes, or what do you recommend? Well,
I mean, in some sense, with probes, you generally get what you pay for. There are some probe manufacturers that are out there, that third-party probe manufacturers that make some pretty good stuff. Whereas is a $20 probe going to be better than a $4 probe? Most likely. But that same probe, if you bought it from Tektronix, might cost you, $200 or more. The Tech probes are actually quite expensive, but they're extremely durable. I mean, I've got Tektronix analog probes that are 35 years old down on my bench that are still working fine. I don't think any of the $20 probes that it would last that long. But then again, it's $20. You could replace them again when you want to, right? And again, if you're just using it as an indicator, the fact that the probe might not be perfectly flat in frequency or something like that, may not really matter to what you're doing. So I would say if you're, $20 is probably even a bit on the high end of these aftermarket probes that you can find on Amazon and eBay and things like that. So if you're spending, $15, $20 on probes, you're probably going to get something that's going to work reasonably well. Okay. If you're spending $4 or $5 on probes, probably not. Okay.
And, at the end of the day, to describe, because we just talked about what they do, we didn't talk about what they look like. So, generally speaking, they have a very sharp metal point on them, and oftentimes there's a collar that goes around them that allows you to attach what George, what did you call the little grabby thing?
Oh, it's like an easy hook.
The witch's hat, yeah.
Yeah, it looks like a witch's hat, and you can press it like a syringe, and this little hook comes out. And then off the side of it, there is a wire, presumably attached to the shield of the coax, with usually an alligator clamp or similar on it for you to attach to the ground. Well, actually, I shouldn't even say that. I shouldn't say that at all.
Well, actually, you probably should. And I was going to mention that. And that's really a very important difference between looking at signals with a scope or looking at signals with a meter, like a multimeter, is that a multimeter allows you can put those two probes anywhere you want in your circuit. Right? I want to measure the voltage across this component or across this circuit. Place your probes there. With a scope, one side of the probe is ground. So you have to worry about that or think about that. If you're working on a circuit that's battery powered, it may not matter so much because it'll just establish, your house is ground at that point, but everything else will just float around it. But if you're working on something that is line powered, or it's got a ground connection through a power supply, that probe connection, the alligator clip portion of it, has to connect to ground because it is ground. And so if you connect it somewhere else, you'll short that node to ground. Or if you're looking at with two channels and two probes, the grounds of both of those probes both have to go to the same ground potential. And you might connect them in different spots on the circuit, but they're both going to be at ground. That's an important difference, when comparing, looking at things with a scope versus looking at things with a multimeter.
Well, I'm glad you said something. Dave Jones, actually, I don't know if you've seen the video where he talks about...
Great video.
Yeah. Really. In fact, I'll take a note to it. But basically, it explains how... And these are the things you don't think about until someone explains it to you. And then when you hear it, it makes perfect sense. But if you're not paying attention to where you are connecting to ground in your circuit and where you're probing, you actually create short circuit opportunities that'll either fry your scope or fry your circuit.
Yeah, I got a good example for that. I was actually, one of the jobs I had before joining Tektronix, I was an applications engineer at another company, and one of my good friends worked in the calibration lab and repair lab. And I was in there having lunch with him one day. And he was working on a UPS power supply. And, there's a big, heavy what look like ground planes and things like that on the circuit board in there, but they're really not ground. And I was just helping him poke around and look in there. And I remember my manager came in, and he was, a bit of a tech wannabe. Okay. And he came in, and he's like, we're kind of poking around. He goes, what about this over here? And he goes and grabs a probe, and just as he's going to connect it up, we're like, no, don't. He connected up to what he looked like a big fat ground plane, which turned out to be one of the supply rails in this UPS. And the thing, the unit shorted out, parts literally unsoldered themselves from the board. Things got really ugly, let all the smoke out of everything. And yeah. Remember that the scope grounds are ground.
Real honest to God grounds.
Yes.
Now, yeah.
I should say there are a small class of scopes where the analog input channels are floating, and they're typically kind of geared towards field use and looking at power systems. But the vast majority of scopes that are out there, the channels are not isolated. The outer shell, that BNC connector, is ground.
So I'm assuming, though, in the $300,000 scope, that's an option.
Oh, no. They're all ground.
Thanks, Alan and Jeremy. Well, that pretty much does it for the first half of our show on oscilloscopes. Stay tuned, and in the coming weeks, we'll do the second half of the Oscilloscope Test Equipment Show. Thanks very much for listening, everybody. 73s.
The Workbench is also brought to you by MCM Electronics, purveyors of everything you need to outfit your workbench, from hand tools, soldering equipment and supplies, meters, power supplies, oscilloscopes. MCM Electronics has these and more tools you'll want to put on your bench. MCM Electronics also carries the parts, components, semiconductors, and modules to help you build your next project. They also carry a wide assortment of Raspberry Pi and Arduino boards and accessories, including stock from Adafruit. MCM Electronics also carries the things you need to help you build your next ham radio go box, such as weather-resistant plastic cases and standard and shallow-depth 19-inch rack flight cases. Find them online at www.mcmelectronics.com, and don't forget to save 5% on your next order with the code RADIO5. That's www.mcmelectronics.com.
and MCM Electronics for all of your equipment and... Please don't air that. Let's just keep that away from the listeners. I will keep going if you'll promise not to play that second one there.